Okay, I'm going to talk about a gauge field thing, and I want to address an intuitive understanding on why and when the magnets can have a final Hall effect. Okay, this was done mainly by these two guys. One is like Masakano, he's doing most of the calculations on magnets, and Ryo Makoto, he's doing something on the SOC Hubbard skirmions. Okay, so let me start from gauge fields and fluxes. And as far as I understand, I mean, this is the first paper I encountered about what the pyrospace is. It was like a very old paper by Affleck and Marston telling that the Hubbard model, if you have a large n expansion, they will get this kind of like an effective Hamiltonian, which will be written in terms of the hopping with the complex coefficients chi. And if they go around the bracket, they're going to get a pi flux phase. And pi flux phase is very interesting because they can have, for example, a Dirac point. And it's also related to the high DC superconductivity at that time. Okay, then the idea here is that people already know that it can be applied to the ferromagnets. And the thing which is fortunate or unfortunate about talking at the end of the day is that most of the introduction parts are taken over by the previous speakers. So I'm sorry for many duplications, but of course you know already about this paper. And also these theoretical papers, three key papers that was written at around 2010. And we also want to mention that there's a non-reciprocity, which is quite recently found in actual experiments on the same, on the ferromagnet in the neutron scattering in 2017. But anyway, all these things are related to ferromagnets. And ferromagnets, we know that it's going to be one of the representative thermal Hall effect sources. And for the simple model, we can think about the Heisenberg and the DM interactions. And once we have a ferromagnet, we have a shrinking with a moment, and that magnon will hop to the neighbor. And for the Heisenberg, it will be a simple hopping, but the DM interaction, they will have an antisymmetric hopping. So together, they're going to have a SU2 gauge field, U1 gauge field. And due to this fictitious magnetic field, which is going to bend the motion of magnets, they're going to have a non-reciprocity and a thermal Hall effect. But then there's a condition for this DM interactions to take place, because if you have this kind of term, d dot x s dot s cross s, it means that the DM vector should couple to the fluctuation of moments, meaning that if we have a ferromagnetic moment pointing in the z direction, there's a fluctuation on the xy plane. And to have that kind of coupling with the d vector, this xy plane cross product with the nearby spins should have an element which is proportional to the d vector. That means that the magnetic moment should be parallel to the d vector. This is one condition that we have to have a ferromagnet to couple to the DM vector. Another rule, which is another constraint for the U1 gauge field up here, is that we need to just select the alignment of the DM vector. So we have two different classes of the alignment. One is the staggered DM, and another is a uniform DM. The staggered DM comes out for the case with inversion symmetry. And if the magnets hop from left to right, they have a staggered up and down configuration. And for the uniform, we have only up, 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 like that. And why we need to have a staggered DM is that if you try to go around the loop, and then we have a uniform DM, it will cancel out by going up, going left and right. And in the end, they don't get a flux. And because the intrinsic property that is important for the U1 gauge field is a flux, not the gauge itself. So that if you have a net zero flux, it will not allow the thermal Hall effect to appear. So in order to get a thermal Hall effect for the DM vector, we have to have a staggered DM in this framework. And if we have a skyrmion, it also generates a U1 gauge field. But in this case, we don't have to have a kind of a serious treatment, because we also always have a net flux, non-zero net flux appearing in this configuration. So the second condition is that we have to be very careful about the alignment of the DM vectors. Now, the third thing is a bit more people have already talked about, is to avoid a flux cancellation. So this is called the no-go theorem, but I have to mention for caution that this no-go theorem is only applied for the ferromagnets. So if you have a flux, U1 flux, on a pyrocarbon Kagome lattice, the net flux is 0. But because the flux has -2 phi and phi on different configurations of the placket, they don't cancel out. But if you have a triangle and a square, they have the plus and the minus flux on the same shape of the placket or the triangle, so that it can easily cancel out by the symmetry operation. So let me just explain a bit more. So if you have a square lattice like this, we can make a kind of a translation by one lattice spacing, and that will convert a plus and a minus location of the flux. And then we can just get a C2 rotation by just flipping the plane upside down, and that would just bring a flux back to the original position. And that will make the Hamiltonian unchanged after these two operations. But then, because we're flipping the planes upside down, it will make the kappa, a thermal coefficient, to be minus. And for both of them to be satisfied, we have to have kappa equals minus kappa, meaning that kappa is always with 0. So this is a kind of a logic that this no-go theorem works for the corner shared, edge shared lattices. But this is only for the flux. So far, and I just referred to one more cases about the U1 gauge field on an incommensurate lattice, incommensurate order. So in this case, we have a whopping, I have a long wavelength configuration of spins, so that, the magnets are always defined conveniently for the shrinking of the moment, so that you can see that the magnet's quantization axis is changing slowly in space. So if we want to just put it back to the global z-axis by making it rotated by the local gauge transformation on each spins, the interactions between these magnets will acquire a phase, and it's going to be a U1 gauge. So this will naturally bring us a gauge into this a kind of a configuration. So that's why we can get a U1 gauge field from this fermion texture, because they will also have a slowly varying spin textures. And indeed, there's a work here done by Akazawa-san in ISB. He showed this is a fermion thermal Hall effect. Okay, so far we were talking about ferromagnets, and after 2010, I think not much has been. There are some advances, but I think people were done with thermal Hall for quite a long time. And then we started to do this business 2017 because I was taught by the experimenters that I have to do some calculations on this. So we started to think about an antiferromagnet. And to go to the antiferromagnet, let's go to the electron first. So the electrons, let's think about the electrons with the spin-orbit coupling. And for the spin-orbit coupled electrons, what we see is that we have an up and down electrons. And because of the spin-orbit coupling, they have to connect a momentum and the spin. And for that, once the electrons want to hop to the neighbor, they have to flip the spins. And for that, we have to have a spin rotating hopping, which is given by this SU2 gauge field. See, they are going to have if one electron is hopping from J to site I, it's going to rotate by some sort of an angle theta, which is determined by the original Hamiltonian, about the angle n, about the axis n. So if the electrons run from left to right, as in the same way as magnets, they have to rotate the spins in order to hop, right? So this is going to give us a SLC hopping, and because in this case we also have an inversion symmetry breaking, we have to have a spin splitting for that. And this is something which was observed for a long time ago in the Rashba and Dresselhaus effect. And this is the spin moment and locking, and the spin splitting will appear naturally for this kind of framework. So the idea is that can we realize it in the insulators as well? And indeed, we can make an analogy between electrons and antiferromagnets. So electrons, we have up and down spins. They will have an SOC coupling. And we have a Rashba and Dresselhaus effect by the spin splitting, right? And that will be the source of the anomalous Hall effect and also the spin Hall effect. Okay, the ferromagnets, as I mentioned, they have a non-reciprocity and they have a U1 gauge thermal Hall effect. But I mean, they don't have enough abundance compared to the electrons. So if we want to go to the antiferromagnets, what we see is that we can have two sublattices, which was mimicking the up and down electron spins, so that if we just regard it as like a pseudo spin, we can couple them by the pseudo spin orbit coupling, and then get the same physics as we did for the electrons. That was what we expected for the first time. So we did this work, but it was motivated by Onose-san's work in 2008. He came to our lab and he wanted me to us to calculate something on this material, and they performed a microwave experiment and they found a microwave non-reciprocity. But so far, he hasn't done a Magnus Hall effect yet in this material. It's like a bit tricky experimentally. But then we were asked to do that, so we made the calculation of square lattice antiferromagnet. And here's a very straightforward model from that material. And we have an anisotropy and the DM interactions. And the DM interactions is shaping in a way that has a Rashba type configuration of the DM vector. Okay. And then what we found is that indeed, without any DM interaction, we have a typical antiferromagnetic degenerate linear dispersions of bands. But then if we just turn on the magnetic field as well as the DM interaction, we have a non-reciprocity. We also have a spin texture that appears because each of these K points carry different orientations of spins. Now, we can also have a topological A state. So, and finally, we get a thermal Hall effect. But the thermal Hall effect is a bit more tricky because in this case, we have to have another trick to get a thermal Hall effect because if you have this like a in-plane antiferromagnet, we don't have any thermal Hall effect. So we have to count off the spins from the plane, as well as we have to prepare a DM vector which is perpendicular to the moment. This is completely different from the ferromagnet because ferromagnet, as I mentioned, they want to have a moment to be parallel to the DM vector, but this is completely different. So we could calculate this, and we could understand a bit, but we did not know what it was, why it was. So we came up with a whole list of all possible configurations between DM vectors and like two different sublattice moments and a field, and it's like more than about 100 patterns. And then it was reduced to only 4 building blocks. And we found out for the 4 building blocks which phenomenon to happen, and this is a list. And you can see that the thermal Hall effect is quite difficult. You can see three crosses, and only one case can be possible to realize the thermal Hall effect. And that was something which we actually found in the previous slide. And at this point, we were not so sure what was happening. The only thing we could say is that, okay, for this configuration, we can get a thermal Hall effect because of the fact that we have 2 species of magnets and they are coupled by a pseudo-spin orbit coupling, which is generated by the DM interaction. And for that, we needed to count off the spins because DM interaction should be turned on because they need to have a fluctuation cross product to be finite and also have a component which is parallel to the D vector. And that is going to be realized for this configuration. And at that point, we wanted to get a general idea, but so far it was like almost, this was like enough at that point. But then we found several examples that should belong to the SU2 framework classes. And after a few years, we met a skyrmion. And this is the main topic for today. So we have an antiferroskyrmion in this material, which was had several nice papers related to this material. The point is that they have a so-called antiferromagnetic skyrmions when they have a field placed at 5 Tesla or something. Then this skyrmion is very complicated. We have a 3-dimensional structure, and they have a slices of triangle lattices. But then, if you just take a closer look, you can see that there are 3 different sublattice skyrmions get together. But they are having altogether this kind of very complicated structure. And very luckily, previous theorists and experimentalists has clarified all the basic properties. What is the Hamiltonian? And what is the parameter that should reproduce the experiment? And then the experimentalists in INSSP Yamashita group, Takeda-san and Yamashita-san, has performed a thermal Hall experiment and actually found a finite kappa xy only at the parameter range where they have a skyrmions. And they want to confirm that y is, if it's like true or not, and they wanted us to confirm theoretically that this is true. So that's why we calculated this for the spin wave calculation. But unfortunately, this has a very large unit cell. And I wanted to make it very simple, but Masa wanted to do it fully. So he did 384 unit cell calculations on the spin wave. So it means that we have more than 300 magnum bands, which is like a spaghetti band. And they have a very complicated Bary phase, Bary curvature distribution, which is colored in different, like you can see this. And then you can get kappa xy by integrating these contributions from the Bary phases, and we actually get a very good reproduction of the thermal Hall effect at this antiferromagnetic skyrmion phase. But now, this is still a numerical experiment. We have to have an underlying vision to get that. So we went with a U1 gauge field theory because we have 3 skyrmions. Each of them are carrying a flux, which is generated by the warping of the textures, right? And if these 3 are decoupled, we can get each of them as a U1 gauge field. We can see a Mickey Mouse-like structure. You can see this very curvature. This is like a vector potential generating the fluxes, which is like B. And this is a counterplot here. And you can see that there are these 3 different U1 gauge fields are just like a translation of 3 Mickey Mouses. Okay, and then, this time we can see that the next flux is again 0. It means that just like a ferromagnet, if we have a symmetry population, that will kill each other. So that with only this V1 gauge field, we cannot get a thermal Hall effect. But in reality, we have a thermal Hall effect. So the reason is that these 3 sublattice skyrmions, they couple in a higher gauge band gauge. If you just make a coarse-grained field theory, we can see that unlike the U1 gauge field case, we have 3 bosons, and they are coupled to each other by the Heisenberg interactions or other interactions as well. And then the low-energy effective theory will be such that we have 3 different bosons. They are coupled by the 3 times 3 matrices that can be described in a 3 by 3 fictitious vector potential. And that is which we call a SU3 gauge field. And because of that new higher rank gauge field, this kind of thermal Hall effect will be arising. I can just explain to you a bit more clearly. So if you simply have a U1 gauge field, which is a C number, it's a flux, right? So with a symmetry operation, they can cancel each other, as I just told you in the introduction. But if you have a higher rank gauge field, it means that this is a matrix, so they cannot commute with each other. So it means immediately that by construction, the higher rank gauge field can get a finite amount of net fluxes on these plackets. And so whenever we get a higher rank gauge field coupling between different sublattices, we can automatically get a finite thermal Hall effect because of this non-vanishing fluxes. And that's basically the rule that we can get. And going back to the condition, when these kinds of SU2, SU3 gauge fields will come out, is such that in the case of antiferromagnet, we can count out the spins to couple these 2 different species of magnets by the DM interaction. That is the necessity condition to get the SU2 gauge field. And for the skyrmions, we have U1 gauge field automatically for each sublattices, and they can naturally couple by the simple Heisenberg term. And this is very straightforward. But for the 3 sublattice Néel order in plane, they will never get a coupling like this, so they cannot have a thermal Hall effect. So this kind of simple understanding will allow us to picturize every different kinds of sublattice antiferromagnetic ordering to be reduced to the very simple picture that we don't need that much calculation, I would say, to understand why this is coming out. Okay, I have several remarks on this. So one thing is that we have done a calculation on a spin wave, and it turned out that it had like more than 300 energy bands. And then I wanted to shrink the calculation. So I just suggested him to take only few energy bands, because if you have a like 0.5 temperature, it's going to just cross only few bands. So I thought that would just reduce the calculation. But then he told me that, okay, we have to include all the bands and this will definitely change the result. It means that unexpectedly, we have to think about a very high energy level for this kind of spaghetti band to get a thermal Hall effect. But in that case, I think Sasha has told us that we have a magnum, the dumping effect. And we don't know whether a higher energy, energy band is very valid for this kind of low energy effective theory. So it's a bit tricky, but still we have this kind of phenomena. Another thing is that I have stressed about the gauge field theory, but if you do simply the gauge field calculation, it does not reproduce the spin wave result. So this is the case of the U1 gauge theory. So the left-hand side, we have a U1 gauge theory energy band, and the right-hand side is also a spin wave on a very similar model. And the band structure is not so different, but the Chern number is completely different, meaning that, okay, the U1 and the SU2 and other gauge field theory can give us an intuitive picture, but it's not so straightforward to really interpret in each Hamiltonian level. So we have to be a bit more careful about that. Okay, I want to address one more thing, because I first thought that it was not restricted to insulators. But anyway, it's an insulating community. But anyway, I have to go back to the electrons to confirm that, okay, magnets can also be valid for some reasons. Okay, so let's go back to the SOC, spin of the coupled Hubble model. This is spin rotating SU2 gauge field hopping plus the U. And if we go to U, it was infinite, as probably Paul has mentioned. You have effective spin model at the second order, which will generate automatically the DM vector as well as a KSAEW term, which is kind of an Ising type of interactions. And this is already well known. And you can see that how these interactions would change by the spin orbit coupling parameter. And this DM vector is following the n vector rotational axis vector from the original Hamiltonian. So they are connected, definitely. And because we were interested in electrons as well, we did a phase diagram calculation on the ground state of these square lattice and triangular lattice spin orbit coupled Hubble model, and found out this very rich magnetic phase diagram. And here you can see that there are circles, which is giving us a sort of a skyrmion in their Hubbard framework. And then we can have a large scale skyrmion even in a metallic state, for example, in a triangular lattice. And in that case, what we find is that in the metallic skyrmion in the triangular lattice, we get a Fermi level, which is on the energy band. And that energy band carries a finite Chern number. And if you see how the spins are carried by each band, they have this very rich spin textures and K-space. And then once we just make U very large, it's going to be connected definitely to the Magnum picture. So we wanted to know how the Hamiltonian is related. So recently we've done a fourth order calculation, which is quite crazy. I'm a bit pity about my students about asking him to do that. But then you can see that the fourth order term includes many, many terms like this. This is only a list. I have a full table in this archive paper I just suggested. And then we evaluated how large is the fourth order term. And it turned out that for U over T equals 4, it's already quite large, the fourth order term. And we included all the terms up to fourth order to calculate ED, the ground state of the effective spin model, and compared with the original model. And it turned out that it's surprisingly giving us a good agreement down to the place where we have probably a metal-in-shutter transition. It means that the fourth order Hamiltonian will give us a good descriptions on the spin the multi-insulating phase of the Hubble model, and they're connected with each other. So we can be much more closer, and the perspectives will be such that, okay, we have like found many things on Magnum picture, and if you just go to the spin model, which is a bit more complex, but then we can just like connect these physics together. So I think I'm done, almost done. So this is a summary of my talk, and I hope I have just dribbled into the picture of how we can get a whole effect. So thank you very much for your attention.